Guys, I'm afraid today I'm not well prepared, so we might have to read this thing a bit together and see where we get along. On the main channel, I don't think they've told us where they're going to go. I mean, they've said where we're going to start from, which was this, because this is what they did at the weekend, but they haven't kind of said what sections they're going to do. So we'll just see how far we get. So it's starting from this section, which is evaluating actions, the credit assignment problem. Okay, so I'm going to start. So if we knew what the best action was at each step, we could train the neural network as usual by minimizing the cross entropy between the estimated probability distribution and the target probability distribution. It would just be regular supervised learning. However, in reinforcement learning, the only guidance the agent gets is through rewards, and rewards are typically sparse and delayed. Okay, so is everybody kind of okay with that? Or does anybody have any kind of comment on that bit as to, I must confess, I'm new to reinforcement learning. It's not one of my, main areas. So, I mean, I can sort of see what they're sort of saying here, which is that rewards are kind of unpredictable and only certain actions will give you certain rewards. Learning using those in supervised learning is not that easy. So that's what I got away from that.
Yeah, and I tend to agree in a sense that when they talk about the reward, that's your final action. So you may have a sub steps to take before you come to a final step. But the final step, once you reach the final stage, it could be either way, plus or minus, whether you're totally wrong and totally right.
Yeah.
So there is like, you don't know what the way where that gradient need to be applied. So there is no one step along the way which is going to give you some answers, I guess.
Yeah, that makes sense. And then they give an example. So, for example, if the agent manages to balance the poll for 100 steps, how can it know which of the 100 actions it took were good and which of them were bad? All it knows is that the poll fell after the last action, but surely this last action is not entirely responsible. So yeah, this is exactly what you were saying.
Correct.
So this is called the credit assignment problem. When the agent gets a reward, it is hard for it to know which actions should get credited or blamed for it. Think of a dog that gets rewarded hours after it behaved well. Will it understand what it is being rewarded for? Okay, so that's interesting. To tackle this problem, a common strategy is to evaluate an action based on the sum of all the rewards that come after it.
Mm-hmm.
Okay, usually applying a discount factor gamma at each step. The sum of discounted rewards is called the action's return. Okay, so you take the sum of all the rewards that came after this action, assuming that this action kind of prepared things for for all that to happen, and you discount the number of steps that were taken after this particular step using this discount factor gamma. Did I get that right?
I'm not sure. To tackle this problem, the common strategy is to evaluate an action based on the sum of all the rewards that come after it. I thought the reward is just one, it's just one stage, and then steps are the multiple. You know what I mean?
So I think the more general.
There are different ways it could be, because like, for example, you can like there are a lot of ways you can formulate this problem. Say you like want to get out from the maze, and you can assign a negative reward for each step you are like you haven't get out, or you can only assign a positive reward when you get out of it. And in both cases, it like theoretically it would work, but probably I don't know. I don't have like any practical experience with reinforcement learning, but I think like the way you formulate the problem should be like making learning easier. And so you can formulate a problem in different ways, and sometimes you have like a reward for each step,
step.
or you may not have reward.
That makes sense. Then, if you for each step, if you award the award, then it makes sense in a sense. Like in finally, where you get into whether it's a positive or a negative, but then you go back and evaluate that what was your reward on each step. I guess. Okay, and then okay, that makes sense. Yeah.
Yeah, so here they give an example. So this is sort of like a picture of it, where you've got a certain number of steps you can go, and so you're saying you can go right again, and there's a fire there. So so it's interesting that they're okay. So yeah, so so this step was a good step, got a reward of 10. This step was a neutral step, didn't get any reward. And this step, because there was a fire on it, it actually had a negative 50 reward.
Mm-hmm.
And then they applied a discount factor gamma of 80% to get the kind of reward at this point, the calculated reward at this point. And yes, okay. So yeah, so this is sorry.
Is the gamma is the factor discount factor for each step, and is that a hyperparameter constant, or does it get changed on every step?
In these kind of descriptions, it's a constant. It's a hyperparameter.
Mm-hmm.
And if you've ever done any finance, there's like a discount rate. Yeah, I mean, I guess it doesn't help you at all if I mention that, because if you don't know finance, but this is exactly how you measure. This is called discounted cash flows. So if you want to measure an investment, you work out how much money it's going to give you, sort of next year and the year after and the year after, and you use exactly these calculations to work out what that's worth for you today. Because the idea is that the money you get sooner is worth more than money far in the future. And that's why you discount it, in that, you might never get to that point because you might drop dead, but, so you discount the most future, further out ones by a much bigger amount than the nearer ones. And this is the same kind of approach these guys are using.
Mm-hmm.
So they give a little bit of a description of what this gamma does for you. So if the discount factor is close to 0, then the future rewards won't count for much compared to immediate rewards. So if you're just doing gamma 0, then all these guys are going to be 0. Only the current step will have any action. Conversely, if the discount factor is close to 1, then the rewards far into the future will count almost as much as immediate rewards. Yeah, so depending on how you choose gamma, you can control how much you value future compared to the present.
Mm-hmm.
Let's say typical discount factors vary from 0.9 to 0.99. And with a discount factor of 0.95, rewards 13 steps into the future count roughly for half as much as immediate rewards, since 0.95 to the power 13 is half. So did that kind of make sense where this to the power 13 came from? Because, yeah. So, yeah, okay, cool. And while with a discount factor of 0.99, rewards 69 steps in the future count for half as much as immediate rewards. In the count-poll environment, actions have fairly short-term effects, so choosing a discount factor of 0.95 seems reasonable. Yeah, so you choose your gamma based on kind of like what the reward functions are doing for you. Okay.
Mm-hmm.
And okay, so of course a good action may be followed by several bad actions that cause the poll to fall quickly, resulting in the good action getting a low return. Similarly, a good actor may sometimes star in a terrible movie. However, if we play the game enough times, on average, good actions will get a higher return than bad ones. We want to estimate how much better or worse an action is compared to the other possible actions on average. This is called the action advantage. Okay, so did that kind of make any sense? So the idea that it's not deterministic what's going to go on, but each kind of path from the current position has got a certain probability. And then it's the average the reward that you're interested in, not any particular specific one. Does that kind of make sense?
Yeah.
And this is called the action advantage. Okay. For this, we must run many episodes and normalize all the action returns by subtracting the mean and dividing by the standard deviation. Yeah, so this is making it into like a normal Gaussian. After that, we can reasonably assume that actions with a negative advantage were bad, while actions with a positive advantage were good. Perfect. Now that we have a way to evaluate each action, we're ready to train our first agent using policy gradients. Did this bit make sense about the fact when the value is negative, it's bad or worse than average, whereas if it's positive, it's better than average? Does that make sense?
Yeah.
Okay, cool. So next we've got policy gradients. So this is, I mean, the whole reason for computing a lot of these is to be able to help to compute the gradients. So as discussed earlier, policy gradient algorithms optimize the parameters of a policy by following the gradient towards higher rewards. One popular class of PG algorithms called reinforce algorithms was introduced back in 1992 by Ronald Williams. Here is one common variant. First, let the neural network policy play the game several times, and at each step compute the gradients that would make the chosen action even more likely, but don't apply these gradients yet. Okay. Once you have run several episodes, compute each action's advantage using the method described in the previous section. If an action's advantage is positive, it means that the action was probably good, and you want to apply the gradients computed earlier to make the action even more likely to be chosen in the future. However, if the action's advantage is negative, it means the action was probably bad, and you want to apply the opposite gradients to make this action slightly less likely in the future. The solution is simply to multiply each gradient vector by the corresponding action's advantage, okay? And then finally compute the mean of all the resulting gradient vectors and use it to perform a gradient descent. Did that algorithm kind of make any sense to people? I must confess I don't have an intuitive feel for how the gradient descent is working, but like overall I can kind of see what they're trying to do.
Same for me. I think I just picked up few bits out of it. Not 100% sure. So what's
Yeah. So we're sort of saying that we've got some sort of function which is choosing an action, and that function's got a gradient. And then so based on these calculations, we can either increase the function towards the higher gradients, or the weights towards the higher gradients if the action appeared to be better than average, or decrease the weights to make that action less likely. And then we use that for gradient descent. But as I say, I don't have a clear feeling for how exactly this works.
Yeah, but we are not applying that gradient descent on every batch whatsoever. We kind of like accumulating it.
Let's see what they're going to do, because they've done some code here now. So let's use TF-Keras to implement this algorithm. We will train the neural network policy we built earlier so that it learns to balance the pole on the card. First, we need a function that will play one step. We will pretend for now that whatever action it takes is the right one, so that we can compute the loss and its gradients. These gradients will just be saved for a while, and we will modify them later depending on how good or bad the action turned out to be. So they've got a function here called play one step. So it's got an environment, some observations, a model, and a loss function. So with TF gradient tape as tape, the left probability is the model applied to the observations, some sort of new and Peter new axis. I'm not sure quite what that's doing, but it's applying the model to something to get a probability on the left. And then the action is if there's a random variable between uniform distribution, if the probability is higher than the loft probability, then you I guess you go left. And then the target value is a constant 1 minus the cast of the action, so whether the action happened or not. And then the loss function is the target and the left probability. And the gradients are tape gradient, the loss, model trainable variables. Okay, so that's the gradient against the loss function. The loss function was the mean of the target and the left probability. And then finally, we return the observations, the reward, done and info using this env step function. Not quite sure what that does. So let's walk through this function. So with the gradient table lock, we start by calling the model, giving it a single observation. We reshape the observation so it becomes a batch containing a single instance, as the model expects a batch. This outputs the probability of going left. Okay, so that's the first bit here. This left probability A equals bit here. So that's that bit there. Next, we sample a random float between 0 and 1. It's between 1 and okay, between 0 and 1. It says 1,1, but okay, let's say assume it is doing what it says. And we check whether it is greater than the left probability. So that's that bit there. The action will be false with probability left probability, or true with probability 1 minus the left probability. Okay, right, fine. Once we cast this number to a Boolean to a number, the action will be 0 left or 1 right with the appropriate probabilities. Okay, did that make sense? That this bit, which is where they're using this random number to decide this action, and so it gives you the with the a certain probability whether the action was done or not. Yeah.
Yeah.
And then said next we define the target probabilities of going left. It is 1 minus the action cast to a flow. If the action is 0 left, then the target probability of going left will be 1. If the action is right, then the target probability will be 0. Yeah, I don't really get that bit, but okay, so why are they calculating the target in this way? Next, we define the target probability of going left.
So
it is 1 minus the action. Sorry?
I think that according to the algorithm, we want to make compute the gradients which make the action which we take more probable, right?
Right. Yes.
So and defining the target in this dynamic way, depending on what the action is, we achieve this goal, right?
Yes, you're quite right. Yes. Oops, sorry. Yeah. So then we compute the loss using the given loss function, and we use the tape to compute the gradient of the loss with regard to the model's training variables. Again, these gradients will be tweaked later before we apply them, depending on how good or bad the action turned out to be. Okay, so we're using now the target to compute the gradient. And finally, we play the selected action. And we then return the new observation and reward whether the episode is ended or not, and of course the gradients that we just computed. Okay, so is everybody okay with that? I think I sort of get it now.
Could you repeat the one which Arto said, the top point? Next we define target probability of going left. What does it mean?
Okay, so the first bit of it was that it kind of decided whether to go left or right using this this calculation here,
yeah,
which was kind of, it was based on a so let's have a look. So the model gave us a probability, so we applied the model to the observations to give us a probability of it going left. Next step was we computed an action value, which was if our random value was greater than the left probability, then that we have carried out that action. Yeah.
Okay.
So this is just a way of saying, you know, the calculation gave us a left probability, but now we're kind of saying, did we really do it? And which was, we randomly compute a number and then check with that. So that's just a way of kind of deciding on. Yeah, I mean, whether left really happened, because we only got a probability of left, where this is now a decision that we definitely did go left. Yeah. Yeah. And, okay, so but to be able to do backpropagation and to calculate any gradients, we need to compute like a loss function. You know, to be able to compare a thing that we did with a thing that we expected to do.
Yeah.
So what we're doing here is we're saying, okay, we expected to do Y target. So this is a way of kind of converting that into a target that we can use. Yeah. And then the loss function is the thing that we did and the thing that we're going to do. Like it's kind of like the same thing, but it's a way of computing the kind of gradient of that. Yeah, because the loss function is when it's pushed back through all the model variables is what's going to give you the gradient across the model. And so what Arthur was saying was that this artificial thing that we're creating, which y-target, because normally y-target would be something you'd be given because this is like supervised learning.
Yeah.
But here we're kind of pretending to create it so that we can get the model to create a gradient for us. And the idea is that we're just gonna pretend that we did the right thing. Yeah.
Okay.
And then depending on whether we did the right thing, we will either apply the gradient in one direction, or if we didn't do the right thing, we apply the gradient in the opposite direction.
Okay. Okay.
Yeah.
So y-target is kind of like we created that was our target based on the action we taken.
Yes. And then and it's really just so that we can compute the gradient.
Gradient, yeah. Okay.
Yeah. Okay. And then they've got some code here. So it says and now they've got they're going to play this multiple times, play it multiple episodes. So now they're accumulating. So for each step, they're applying the model. So to play one step, so they do a whole load of steps, and then they append into the rewards the gradients that was calculated. And then all rewards append current rewards, all gradients append current gradients. So yeah, so this is like an accumulation of all the rewards and all the gradients. Yeah, so just through all these different, lots of different kind of, because this is all probabilistic, they're computing like a whole number of runs, these rewards and gradients, yeah? So this code returns a list of rewards, one reward per episode containing one reward per step, as well as a list of gradient lists, one gradient list per episode, each containing one tuple of gradients per step, and each tuple containing one gradient tensor per trainable variable. So yeah, basically all the data that's been accumulated. The algorithm will use the play multiple episodes function to play the game several times, for example, 10 times. Then it will go back and look at all the rewards, discount them, and normalize them. And this is the calculation we were talking about earlier. So looking at the rewards and normalizing them. And to do that, we need a couple more functions. The first will compute the sum of the future discounted rewards at each step. And the second will normalize all these discounted rewards returns across many episodes by subtracting the mean and by dividing by the standard deviation. So here we've got the discounted rewards. So it's got a rewards and a discount factor. And the discounted is first they convert the discounted into rewards. And then for stop in range, length of rewards -2, -1. Okay, they're doing something a little bit funky there. And then discounted at a particular step is discounted at the step +1 times the discount factor. And then the step is going from the final length -2, so not the very last one, but one before that, and going back by 1, step 1. I guess that's what that bit is saying. I'm not quite sure, but yeah, it seems to be walking back from the end to compute these discount factors. And then they're normalizing it, so you're computing the discounted rewards, and then you're computing the mean and the standard deviation, and then subtracting the mean and dividing by the standard deviation to get it normalized. Is everybody okay with those two functions so far?
Yeah, fine.
I know this spell kind of following it exactly might be a bit tricky, but intuitively you can sort of understand that this is discounting all the rewards. Exactly how it's doing it and walking back is a little bit hard to understand, but that's what it's doing. Yeah. And then they're just running those functions. The call to discount rewards returns exactly what we expect. You can verify that the function discount normalized rewards does indeed return the normalized action advantages for each action in both episodes. Notice that the first episode was much worse than the second, so its normalized advantages are all negative. All actions from the first episode will be considered bad. And conversely, all actions from the second episode will be considered good. We're almost ready to run the algorithm. Now let's define the hyperparameters. We will run 150 training iterations, play 10 episodes per iteration, and each episode will last at most 200 steps. We will use a discount factor of 0.95. So these are the hyperparameters. So this is the discount factor 0.95. We also need an optimizer and the loss function. A regular Adam optimizer with learning rate 0.01 will do just fine. And we will use the binary cross entropy loss function because we're trying to get a binary classifier. There are two possible actions, left or right. So we've got the Adam optimizer, and the loss function is a binary cross entropy. And we're now ready to build and run the training loop. So for iteration in the number of iterations, all rewards and all gradients is play multiple episodes, and you're playing the number of episodes you want in that, and then all final rewards, you discount all the rewards, mean gradients, and then go through each of the model's trainable parameters. Then you do the final reward times all the gradients, the step, and then for episode index, final rewards in enumerate, for step in enumerate rewards, access to all mean gradients, append the mean gradients for each of the variables, it looks like. All mean gradients. And then optimize to apply gradients, zip all mean gradients, model trainable variables. Yeah, I can sort of intuitively see what this is doing. So it's run all the episodes, computed the gradients, and this is where the reward is being multiplied by the gradients. So, and that's what they said, because it's been normalized, negative values will get the gradient pushed towards the negative direction, and positive will be towards the positive direction. And they're applying, using the optimizer to apply all of that. So, I mean, the code is a little bit hard to understand, but intuitively, yeah, I think I know what it's doing. Is that okay, guys, or is that still a bit confusing?
It's fine.
Yeah. So let's walk through this code. At each training iteration, this loop calls the play multiple episodes function, which plays the game 10 times and returns all the rewards and gradients for every episode and step. Then we call the discount and normalized reward function to compute each action's normalized advantage, which is the code we call the final reward. This provides a measure of how good or bad each action actually was in hindsight. Next, we throw each trainable variable, and for each of them, we compute the weighted mean of the gradients for that variable over all episodes and all steps, weighted by the final reward. And finally, we apply these mean gradients using the optimizer. The model's trainable variables will be tweaked, and hopefully the policy will be a bit better. And we're done. This code will train the neural network policy, and it will successfully learn to balance the pole on the card. You can try it out on the policy gradient section of the Jupyter Notebook. The mean reward per episode will get very close to 200, which is the maximum by default with this environment. Success. Research, so tip, researchers try to find algorithms that work well even when the agent initially knows nothing about the environment. However, unless you're writing a paper, you should not hesitate to inject prior knowledge into the agent, as it will speed up training dramatically. For example, since you know that the pole should be as vertical as possible, you could add negative rewards proportional to the pole's angle. This will make the rewards much less sparse and speed up training. Also, if you already have a reasonably good policy, for example, hard-coded, you may want to train the neural network to imitate it before using policy gradients to improve it. Okay, so that's interesting. The simple policy gradients algorithm we just trained solved the cardpole task, but it would not scale well to larger and more complex tasks. Indeed, it is highly sample inefficient, meaning it needs to explore the game for a very long time before it can make significant progress. This is due to the fact that it must run multiple episodes to estimate the advantage of each action, as we have seen. However, it is the foundation of a more powerful algorithm, such as actor-critic algorithms, which we will discuss briefly at the end of this chapter. We will now look at another popular family of algorithms, whereas PG algorithms directly try to optimize the policy to increase rewards. The algorithms we will look at now are less direct. The agent learns to estimate the expected return for each state or for each action in each state. Then it uses this knowledge to decide how to act. To understand these algorithms, we must first introduce Markov decision processes. So I think we might stop there because I have a feeling these guys are only going to get that far. If for some reason they get further, I don't know if you guys fancy having a little session a little bit earlier on Sunday before they start to go through it, but I don't think they'll get this far because Markov decision processes are actually quite complex. I wouldn't attack them in the same session as the other one. What do you guys think?
Yeah, fine with me. Yeah,
Yeah, that's
absolutely. I didn't read it.
Yeah, I read through it, and I know a tiny little bit about it because I've done some of it in linear algebra. But yeah, I mean, there's quite a few equations in here which are not intuitively, well, intuitively you can, you know what they're doing, but like trying to work out exactly what they're doing is not easy. So yeah, hopefully the guys on Sunday, there might be some Markov decision super genius who will explain it to us.
Yeah, and I guess there are 3 weeks assigned to this whole chapter.
Yeah.
So 6
Yeah, I mean,
sessions.
there's not much left. I mean, if I look at the sections, yeah, there's only, oh, mind you, yeah, so we've got Markov decision processes and Q-learning. I think those are going to be quite big. And then there's implementing deep learning, and I'm not sure that will take that long. And then it's the TF agent stuff, which is the next chapter. So yeah, I have a feeling they'll probably get on into this bit.
Yeah, I think it's fine. Yeah.
As a worst case, if they do it, I might have to watch the session tonight before Sunday session.
Yeah, that's fine with me. Yeah.
Right. Well, have a nice evening, guys, and hopefully I'll speak to you soon.
All right.
Thank you.
Right.
Right.
So,
Bye.
yeah, one question about
Yeah.
tomorrow's session. Would we have it as planned?
Yeah, I've still not gotten the parallel side of it, but I can do the main jacks. So I don't know if it's still worth doing that. I think, okay, let's do it because I'll just cover the main jacks and flags library because it seems almost like the parallel processing is all part of Google's internal infrastructure and what they've implemented. And I don't think they've actually released that because I was looking for documentation on it. And but yeah, let's go ahead and I'll see if I can find out some more tonight. But we can at least do the jacks and the flags main libraries anyway.
Yeah, sounds good for me.
Okay. Yep. Speak to you tomorrow then.
Bye.
Right.
Thank
bye.
you.